Right, I think I'm going to get started anyway. Okay, thanks everyone for coming. Bit of a warning, as you might notice, my voice is going. So if halfway through this I have to stop, then I have to stop. But this is the third time I've tried to do this, so I'm gonna do it this time.
Always use interpretive dance.
Yes,
to get your message
because that always comes up really well on a screencast. Okay, so as some of you, well, one of you will know, two of you will know, I used to work on a lot of asynchronous stuff, a lot of real-time data processing, pushing data through systems and stuff like that. So I had a bit of experience of this thing. I'm not going to claim to be an expert at all, but I learned a lot of things the hard way. And given that asynchronous and parallel things are both stuff that we're doing a lot more of now, I thought it'd be pretty handy for everybody if I shared some of that experience. Also, bear in mind that some other people in this room have also had experience, so if you want to ask them questions.
I purged it.
The moment you left, you'd already started purging it. Okay, so I'm going to do a bit of talking about what asynchronous is, what parallel is. They're probably not the dictionary definitions of those words that I'm going to use, but they are kind of my definitions that sort of work for me and are quite helpful for me. But then I'm going to talk about why they're important, what different types there are, why it's important to know the difference, what effect that has on your code. Then I'm going to talk a little bit about giving some actual tips and best practices that I've found. And then a couple of things that will kick you in the arse 5 minutes before a deadline. You just need to be aware of. And it's kind of, towards the end, it kind of trails off in importance. So if we do overrun, which I don't think we will get anywhere near, then it doesn't matter if we lose a bit off the end. Okay? It does nothing. Hello. Well, it was working a minute ago. Oh, something happened. Hey! Okay. So, what are asynchronous and parallel things? Both are kind of techniques to aid performance of your code or your system. But they're not the same thing. They are kind of different approaches to the problem. And they often come together. So you may use some parallel and some asynchronous things at once. So, asynchronous is where you start at some sort of I/O operation without waiting for it to complete. So you can carry on doing some other work before it finishes completing. Now, our I/O operation can mean a lot of things. It can mean disk operations, network operations, drawing to the screen, USB stuff, things like that. But it can also mean talking to other processes that are running on the same computer. So inter-process communication, maybe an asynchronous thing, or even if you're using something like Erlang. A language like Erlang, which kind of has the idea of everything is asynchronous anyway, then even objects within the same process can talk to each other in an asynchronous way. Now, so that's asynchronous, whereas parallel is trying to do multiple things at the same time. So I generally use the idea of if you've got threads, then you're doing it in parallel. When I spoke to Julian about this, he sort of shouted me down a little bit. Like, oh, well, you can do things in parallel without threads. You can, so you can have a list of things you're doing and sort of do them all at the same time like that. And do a bit of one and then do a bit of another and do a bit of another. And you're kind of doing multiple things at the same time, but it's not actually a particularly useful definition that it's sort of true. So the example would be when for people who are using Node, when you've got multiple requests, you are doing multiple requests at the same time, but you've only got a single thread, so you're not actually ever working on two of the pieces at any one time. You're only ever working on one of those requests at any one time. Okay. I should also say, if anyone has any questions or anything, feel free to take over the whole presentation.
Does that differ from the way Erlang is written?
So I don't probably know enough about Erlang to answer that in a useful way.
You're running it now.
Yeah. All right. Alright, okay.
Okay, so talking about how we do more than one thing at one time. So this is basically how threads are scheduled, really. There's 3 different mechanisms that threads be scheduled. There's one that's quite an old school way of doing it. It's called multiprogramming. It's a terrible name. No idea why they call it that. Basically what that does is the operating system will say, I'm going to run this piece of code here, and I'm going to keep running it until it starts to do any kind of I/O operation. And the moment it starts doing that I/O operation, I'm going to take the CPU off that piece of work, that thread, and give it to another thread, and let that go. And then that one will carry on until it starts an I/O operation. It's got interesting behaviour that if you've got something that's like a busy loop that sits there constantly using the CPU without any I/O, then that thread will run forever. And no other threads will get any CPU whatsoever. Not many systems kind of use this nowadays, but it's an interesting one to think about. It's also interesting because it kind of relates to Node.js a little bit. So the one that's a bit more recent, but is also making a bit of a comeback, it's not what people use generally, is the idea of cooperative multitasking. And that's where a thread will do some work, and then it will go, okay, I've had enough now. Tell the operating system, I've had enough, you go and let somebody else have a go for a bit. And let another thread in the system have a go. And then the operating system will go and pick another one, and then it will give in. And that also allows you to starve other threads as well. And the starving of other thread is why this third idea, this preemptive multitasking, became very popular sort of in the 80s and 90s. With things like Windows, obviously, and even some of the task-based systems for Linux, obviously, kernels adopted this approach as well. What preemptive multitasking is, it gives a thread a bit of time on the CPU, and then the operating system says, right, you've had enough now, and stops that thread. Stops it exactly where it is, whatever it's doing, stops it, and then goes and gives some CPU time to the other one, to another thread. And then so on and so forth. They keep doing that with all the threads, and then eventually the first one will get to some time again, and run like that.
Presumably it can't stop it in the middle of something like, I don't know, updating another object. It can't stop a thread executing, putting it in a position where it may leave something in an invalid state.
That's generally up to the programmer to specify what that is. So you can. There are cases where you can kind of take over, but you can actually say that. So there are atomic operations as such. Generally, unless you're an operating system programmer, you will never come across those things. Most preemptive multitasking systems, you only assume a single operation is atomic. But that does mean, actually, if you do an instruction, and then you've got another instruction, and that leaves it kind of in an invalid state, then it will be in an invalid state. So if you've got a call that updates multiple fields within a class or something within an object, it can swap out. The operating system can say, no, sorry, halfway through that, and leave that object actually in an invalid state. That's quite an important piece, actually. And it also kind of comes round to why, while preemptive multitasking was very popular for certain systems where there was a low number of users and not much concurrency actually needed, people are kind of moving away from that idea now because it has a lot of problems, like leaving objects in inconsistent states. You end up having to do lots of protection in your code to prevent things from falling over, and it's also quite expensive, which I'll come back to in a little while. Yes, you can have things in an invalid state, whereas the other two actually will always leave. The state the things are left in is completely down to the program, whereas the other one is pretty much down to the operating system. Okay. So here's a bit of code. This kind of tries to give the example of why knowing the difference between these three is actually quite important. It's a bit of pseudocode. What it's doing is it logs number one. We'll assume logging isn't an I/O operation. It's all here. It writes one to the console. It's a bit JavaScripty, this. And it does an I/O operation, which goes off and does some work, and comes back, and when it comes back, it will log number 2 to the screen, and then outside of that, it logs number 3. So, does anybody not understand what this code is kind of doing, really? So 2 is a callback to say once the I/O operation is finished, we'll write 2 out. And there's 3. So those 3 different types of asynchronous or parallel models will give different outputs for this code here. Does anybody want to give a guess as to what something like Node would give in a... actually, no. Anyone want to give a guess what Node would do? Yeah. Sorry?
1, 3, 2.
1, 3, 2. Yeah. Anyone else say? Yeah. Stack trace. Anybody got any different thing to that?
Depends what do I/O operation does.
That's actually true, but let's assume it does. It goes off and does an I/O operation.
So it's properly async.
Yeah.
Then what Paul said.
1, 3, 2. Yeah. Okay. And that's because if I go back a minute, which one of those 3 do you think Node is in practice?
Cooperative multitasking.
Anyone disagree with that? Cooperative multitasking.
First one.
First one. No, it's not the first one. It is actually cooperative multitasking. So if it was the first one, you'd actually get different behaviour. You would actually see 1, 2, 3. In fact, actually, what you'd probably see is 1, 2, and probably never actually see 3. Depending on some subtleties of the behaviour. And that's because you're starting an I/O operation. Look what the first one is. Multiprogramming.
There is another one.
It starts the I/O operation, and then it takes the CPU off that immediately and says, "Nope, sorry, no more. You're not doing any more work."
Would you actually see 2 then? Would it ever finish?
Should it just be 1 then?
So it finishes, and then you have to wait for something else to give up the time, and then you would get 2.
And then 3.
Yeah, and then yes, you would probably get 3 afterwards. It's the details of which order you get 2 and 3 are a bit messy, but you. No, it's not true. The details of whether you would get 3 are a bit messy, but you would definitely see 1, 2 in that order. You would never see 3 before 2 in a multiprogramming environment. But those of us who program in Node.js will notice it's actually a cooperative multitasking, which means it writes out 1, it then goes off, tells it to go off and do the I/O operation, and then writes out 3. And at some point later, 2 will come out because the I/O operation is completed. Now, anyone want to hazard a guess what the output would be in a preemptive multitasking environment?
1, 2, if we've got enough time.
Yeah, that's
Any advance on 1, 2, 3?
Well, 1 definitely first, and then who knows between 2 and 3 because it's up to the OS.
Exactly, that's exactly right. It will be 1, and then you'll either get 2, 3, or you get 3, 2. And there's nothing specified in this code which will explain which way it is. And that's because the operating system is completely in control as to which bit of code actually gets to execute. So if you've got a very, very fast I/O operation, it may switch to doing that I/O operation before it actually gets around to writing out 3 onto the screen. So this is why it's quite important to know the difference. Dotnet is generally a preemptive environment. It has some clever things in sort of 4 onwards, .NET 4 onwards, so you can sort of specify what behaviour you actually see in practice, which is quite nice. But .NET and C# environments generally like that. Almost all things except for Node, really, are preemptive nowadays. It tends to be a thread. It tends to be a pool of threads, and it just executes whatever code happens to need executing at that time. Node with its single threading model is actually much more. It's much easier to know what the order will be because it'll be very consistent. Any questions on that? So there's a bit of talk about why asynchronous stuff is quite important. So that the turns out threads, which were a model which became, as I said before, became very popular in the 80s and 90s as a way of scaling things out. So if you want to do 3 things, you spawn 3 threads, was generally what you did. Problem with that is it doesn't scale very well. Threads are very expensive. I did some experimentation in my last job with exactly how expensive they were. Microsoft claimed that a .NET thread uses 4 meg of memory if it's doing nothing at all. If it's got absolutely no objects associated with it, no registers, no thread statics or anything like that, use 4 meg of memory. I actually found in practice it was near 16 meg. So if you're trying to do 1,000 requests at a time, for example, and you've got 1,000 threads, that's not a lot of memory left. So it doesn't scale very well. Every single thread has to have a stack object. Everyone not know what a stack object is, what a stack is. Okay.
A frame on the stack, you?
Just a whole stack.
All right.
So every thread has to have a whole stack of its own. Also, because it switches mid-operation, any registers on the CPU have to be stored as well. They take up space and time to switch. Thread statics, I don't know if anyone's come across thread statics before. Generally don't use them, they're an absolute pain in the backside, especially in .NET. Basically they are, static variables are just globally accessible. With thread statics, you get a different instance of the object, of the pointer or reference, whatever, for each thread, which can be quite useful sometimes. I mean, if you want to if you're doing a thread per request, you can actually put some request-specific information there that's kind of globally accessible. So it's a good way of cheating sometimes and getting around bad architecture. But they all have to be stored. There has to be one of those for each thread. To create a thread static, there has to be allocated for each thread. And also the startup time of threads is very high as well. Actually starting a thread up, because it has to allocate all these things, is quite an expensive operation. So if you're going to spawn 1,000 threads, I mean that's going to take, I tried it on an old CPU, about 100 threads once. It takes about a minute in total to do all that. Depending on how old your CPU is, but I suspect modern CPUs with modern frameworks it's probably more like 10-15 seconds, but it's a long time. That's why they have thread pools where it starts up the threads for you in advance, so you just have to pick one off the pool, and then they use up a hell of a lot of memory, so not bad. And as I say at the bottom here, idle threads are very expensive because they're doing nothing but costing you a lot. They're providing no value, but they're costing you a lot. So if you've got a thread which is sat there doing absolutely nothing, but just sit there with no work to be done on that thread, you're still paying the expense, but you're not getting any benefit. And where this comes into why asynchronous is important is because if you've got a blocking I/O call that says go and fetch this file from the disk or whatever, and just leave this thread just stuck in its current state until that I/O operation completes, nothing else can use that thread. It's just sat there taking up resources, giving you no value at all while you've got this I/O operation. You can't even put it back on the thread pool and reuse it for something else. It's just stuck there. So threads are really expensive. And what doing things asynchronously allows you to do is basically put the thing back on the thread pool or give control back to something else. To say, actually, why I'm going off and doing this file reading, or why I'm waiting for this result from something else, go and do this work over here. Yep. So you're getting value for your cost then. You're allowing that thread and all those resources to actually do something else rather than just taking up space. So that's quite important. That's also why things that don't have multiple threads and work very asynchronously tend to be very low on resources. So Node.js, keep using as an example, because it's a single thread and everything's off an event loop and pretty much everything is asynchronous, it's very, very cheap to run. It also means that it scales in a very linear way. You kind of get a really good idea what your performance is going to be right up until the point where you start basically not being fast enough. But you're not going to spend loads of time trying to find some memory because you've got thousands of threads and stuff in Node.js, because you're just never going to get in that situation. So it scales in a much nicer way, gives you much better performance generally when you've got high loads and things. So is there any kind of questions on what the difference between async and parallel is before I get into this and why it's important? Does that kind of come across? Anything I need to talk about? A couple of blank looks, but everyone looks bored. Steve disliked it so much he's leaving.
Can't stand node, can't keep picking it up.
Okay, so I'm going to talk about some tips and kind of best practices and things. These are things that I found. Some of these quite interesting because as you do things, especially as you do more stuff asynchronously, it's actually quite difficult to program, as I suspect a few of us have found. Programming in an asynchronous way is a bit unnatural because the code, as we saw from the example, doesn't always execute top to bottom anymore. It kind of jumps around a bit. You have to think about what the state of things will be and stuff like that. So I'm going to go through these tips and kind of talk about what I mean by them and explain how you can kind of put it into your code. So the first one, I think this is probably the most important thing of all, is you should always treat the bit that executes stuff asynchronously or in parallel as its own responsibility. So if you're thinking about single responsibility principle, you put the bit that only does async or only does parallelism in one class or in one object or one unit, and you treat that as a whole separate thing. You test it separately, and then you write your rest of your code as if it's not running asynchronously and in parallel. That just makes your life so much easier. It's just unbelievable how much easier it will make your life if you do this approach. So if you think about what that means, it means that you can, all of your testing and everything doesn't have to worry about threads or async or parallelism with all your objects, except for that one piece. You know, if you've got, again, I'm going to go back to the web browser, web server example. If you've got a whole bunch of requests going, and you've got every single object in your system has to worry about, well, I might actually be doing these two requests at the same time. That's going to be hideous code. It's going to be an unmaintainable mess. But if it's all handled in one place, and the rest of your code just says, no, I don't care about that, it makes your code much, much cleaner, much easier to handle. It's, I think most frameworks pretty much do this for you, which I'll kind of come down to later on. Certainly, you know, the ASP.NET obviously supports multiple requests on multiple threads. You don't know it's doing it most of the time, unless you accidentally use a global object somewhere that it's mutable state, which is a bug we found recently in our code, which is going to trip you up over. That's another example, actually. That's another case of where this is a good idea. If you've got something that is going to be shared across multiple threads or whatever, that's when you suddenly start thinking about these things again. It's like, oh, what if two threads try and access this same thing at the same time? It gets quite complicated. So if you can put everything in a box, that also means don't make things global, because you're immediately taking it out of that box as well, because it then becomes shared across the requests. Kind of thing. Hi, Joe.
Hi, Andy.
So, any questions on that? I haven't got any code to show, unfortunately, for a lot of these. I have probably I'm going to go through some of the framework documentation a bit later on if we need to. Okay, next big tip is always fire a completed event. This probably sounds a bit stupid because you're going to fire a completed event, but actually, what is a completed event can be quite difficult to understand. So if you've got something that's going off and reading a file from disk, and it says, oh, here's a bit of the file, here's a bit of the file, here's a bit of the file, in a kind of asynchronous way, then you need to know that it's finished. You need to know that there is no more file coming. So you need to be able to react on that. And that's a bit of an obvious example. But what if you've got something that kind of doesn't finish? So if you've got something that's just getting a stream of events from some source that's never going to end, like our logging off the site. So you get there was a request happened, there was a request happened, there was a request happened. Do you need a completed event there? Well, I say you do actually. I say you do need a completed event, even though it may never actually be fired in your production code. Try writing tests without a completed event. It's a nightmare. If you're trying to test that your code is behaving correctly, and especially if you almost always end up writing some kind of negative test on these things. Almost always end up saying, if this case happens, then I shouldn't get an event. That's an impossible test to write. I've tried it. I've tried to put sleeps in and waits for long enough and those kind of things. You end up with very slow and brittle tests. Don't do it. So, your completed event in that case becomes, have you kind of unsubscribed from it? Have you closed down the connection? Then you fire a completed event that says, actually, we're done now. You're not going to get any more events from us. Okay. That makes sense? Okay. Okay, so the third kind of tip I'm going to talk about is use the framework or use the library that somebody who really knows what they're doing has written. It's probably a better way to phrase this. This stuff is hard, really difficult to get right and get to work well. If you ever want to get really scared, go and have a nosy in the task object. Go and decompile the task object in Dotnet and get the source code from it. It's a very simple to use object. The code in there will fry your brain. It's the edge cases it has to deal with are just unbelievable. It feels like a really simple thing. So, these guys are professionals paid to think about this stuff, and this comes from a lot of experience and practice. Generally, you're not going to think of every one of those edge cases. If you use frameworks, there's a good chance that the collective software developers in the world, if it's open source, or Microsoft or Sun or whoever it is who's written the framework, are more likely to have thought of all these random edge cases that you haven't. Plus, it's also a common language that all people who are going to look at your code later on can look at it and go, actually, yeah, I know what a task object does. I know how it behaves, or I know how a promise works in Node. I don't need to look in the code to work out any edge cases. I know what the behaviour of that's supposed to be. Just makes your code much easier to read, much easier to manage, and it will cover all your edge cases, or most of your edge cases. Okay. Anything else? Okay. Fourth one of my list of things is don't expose internals that need controlled access. This has got a hell of a lot of those edge cases I've just talked about in it, just in itself. So, it talked a little bit about globals earlier, and how as soon as you've got a global or a static or whatever, you suddenly have to start thinking about what happens if multiple threads or multiple requests access that at the same time, or modifying it. You have to think about, well, what value should it get if this thread over here wants this value? What should happen? As Andy pointed out, what happens if the thread switch happens halfway through a transformation of the state of that object that leaves it in an invalid state? What happens if another thread comes in and goes, actually, I need to read the values of that state for that object? So, so you could sit there and have everything that uses these globals or whatever shared values there are, and put control code around that and control logic in every single client of that code. Or you could actually just wrap it all in a single object and let that object handle the controlled access. Generally, that is the better solution. Let one object, with one class, be responsible for hiding the intricacies of those objects, of that internals of that object from everything else. It's generally a good idea, as I'm sure most of you know anyway, but it's become considerably more important when you've got multiple things going on in the same system, the same memory space, because you can have these issues where things can get out of state and fall over and stuff like that. there's a slight other side of that, which is if you've got one of these like an object that's wrapping this stuff, make sure if it returns any values that those values are immutable or are copies. Don't return direct references to the internal state. As I think, I don't know if Paul Clarkin remembers this one, that when we had the issue where we kept getting the currency list was getting corrupt all the time. So we had this thing that read all the list of currencies from the currency service, stored it internally, and then just gave it out to any request that needed it. And we just basically returned the internal list object. And then turns out one of the clients of this thing was occasionally sorting that list using an in-place sort. And it turns out if that client was being executed on 2 threads, you had 2 threads both trying to sort the same list. And we ended up with lists without GBP in it, or I think Korean, whatever the Korean currency is. Yeah, we had one particular instance where the list we had 8 Korean ones in it, and things like that, and it just completely screwed up. But worse, because it was an internal thing, that then changed the internal value. So everything else that requested the list after that also got the corrupt list. So it was basically the whole system was in a dead state. It was stuck there. The solution to that was to return an immutable list back from the. So take a copy of that list and return that, or actually. You can there's a read-only list for in .NET which you can use, which is actually pretty horrible, to be honest. It's a really bad implementation, but it is read-only. It throws an exception if you try to mutate it. Would have been better if it just didn't have the mutate methods on it. Unfortunately, that's a historic decision by Microsoft. So it's a great example of why immutable values really are your friend when you're talking about multi-threaded systems and doing things in parallel. They save you a lot of pain, but they do require you to rethink a little bit about how you write your code, because obviously you can't mutate them. They're worth the effort. Okay. So the last kind of best practice tip I'm going to talk about is this the .NET sync objects. Now, has anybody actually used these things? Now, I'm actually going to go find the documentation for them. Anyone used the C# lock statement before? Yes. No, you not. This thing here. This thing. This is a great idea, absolutely terribly implemented. How do we zoom on this thing? Make that a bit bigger for everybody. So, that's not very good, is it? Okay, so this is some Microsoft code showing you how to use the lock. And what this says is, come into this withdraw method with a decimal amount, and you're going to lock on this object here, called this lock, and you'll notice it's actually explicitly an object. Usually it's not a sensible thing to do, to just do a new object. It's not something you would do because it's an object that doesn't really have any behavior. It's a bit like doing just curly braces in JavaScript. It's just an object that doesn't have any behavior, except in .NET you can't add anything to it later, so it really is an object with no behavior and you can't do anything interesting with it. Except you can do this thing. So some bright spark in Microsoft decided that every single object in .NET can be used as a lock object. And I must admit, I have no idea why they did this, because it's just stupid. They should have really just said, had an explicit lock object, which is the only thing you could lock on. And the reason why that's quite important is because here's a bit of code. locks on that thing, does some work with this balance object. Okay, does some changes to that balance object and comes out. And what this actually means is if there's a thread switch at this point in here, after this if statement, okay, and then something else comes and it wants to withdraw some amount from the same thing, then you've got a bug in your code without the lock, because it can come in and change the amount after the if's gone. So you can get in a situation where you can actually get a negative balance if the lock isn't there. But the lock says if something else, if another thread has a lock on this object here, don't let any other threads in. They'll come to this point and they'll go, no, I can't actually get any further with this code, so they'll context switch to another thread until it comes out of this stuff, and then it'll allow the next thread in. They'll kind of queue up all the threads that will come in, and that'll prevent the bug. But what would happen if, so Microsoft have done the intelligent thing here of creating a specific object, which is what I would recommend doing. But what happens if we'd used balance here? Code would have actually read a little bit better, and that was their original intention, that you can put lock balance, and then you're saying you're locking control of the balance object. Brilliant, you're locking control of the balance object. That's great. Okay. But what happens if you have another method on here which return the balance? Okay, so something else that returned the balance, then this, okay, technically speaking this is a value type, but let's pretend it's not a value type for now. Let's pretend it is an actual C# object. You're letting it out of the control of this class then. You're letting that internal state again out into the rest of the world. Now what happens if the user of this account object decided it also wanted to lock balance for something? It also wanted to lock on that same object. You can then have some horrible deadlock situations where you've got a thread that's trying to lock the object in here, and then the object exists somewhere else in memory, as access is accessible from somewhere else in memory, and it's also trying to lock on it. It's a great way of putting very, very hard to find bugs in your code. So, to make sure you never do that, I would always recommend that you have an object that its entire reason for being is for controlling access to other objects. So that way you're never going to accidentally leak this out, because all you ever do is lock on it. In fact, actually, I think, what was that tool we had at Waters that did a lot of static analysis?
Coverity.
Coverity, yeah. It's quite a decent tool sometimes. And what it did some static analysis on your code, but one of the pieces of static analysis it did was it would actually track every object that you lock on and told you if it ever leaked out of that object, that class, the containing class, in any way, and then would try and track to see if anything else locked on that. And that was a critical failure if it did. If it just leaked out and it couldn't find anything else, and that was just a warning, you probably shouldn't do this. It's a great piece of kit for that, actually. Found some interesting bugs that it did that. But, so there actually, there are tools that will kind of tell you off for doing this, for not doing that. In fact, I think it actually had a warning on anything that was an object as well, if you tried to lock anything that was an object. I'm now going to show you the worst violation of this.
Before you go away from that one, I've seen that done a lot with you lock on the type. Is that good or bad?
That might be a Java thing, you can't do that in C#.
Or type off.
Ooh. Yeah, don't do that.
I couldn't see why.
That's basically locking on a global, because type of always returns the same object and the same type.
Yeah.
That's a great way of making your code broke. Yeah, don't do that. And I think actually Dotnet does that in a few very specific cases to do with the way reflection works and stuff. But generally don't do that. It's bad. I'm not going to show you the worst violation of this particular that I've ever seen. Sync. I think it's called Sync. It's called Sync object. definitely called sync something. Sync root, here we go. Worst violation of this I've ever seen. Guess who does it? Microsoft. Yeah. So, is that C#? Yeah. Okay. So they had this genius idea that collections would have a sync root. And this is actually an object, actually, but what they do is they make this, is it protected or is it public? Please tell me it's protected, not public. So they have this sync root, which is an object that iCollection has on it, that is supposed to be used for synchronization of all derived types that derive from list. And because it's protected, you basically have multiple classes that have to use it. It's kind of the recommended thing you do if you have a derived type that you need to sync around. I think their original intention was that if you wanted to make it like a list class completely synchronized, so you only ever have one thread in it, then you could actually just lock on sync root in all of your methods. Except it would mean that you would have to completely replace the entire implementation of list to do that. So what the hell is the point? You just write your own list. It is absolutely ridiculous. God knows why they've done it. I think they're too embarrassed to actually put it as deprecated. They really should. It's just hideous. Yeah. So never ever use that. If you're going to write something that's basically a synchronized list, which guarantees that only one thread ever mutates the list at any time, just wrap a list. Just do the business logic you actually want to do with the list, put that internally, and don't expose list operations. Just use good OO practices to prevent us not do that in the first place. But yeah, that's very embarrassing for Microsoft. I don't know why they obviously too embarrassed to remove it because it's just ridiculous. If you look up the read some of the things on blogs about this and Stack Overflow, people just say, "What a bunch of idiots! Why have they done this?" It's quite amusing. Okay. So, okay. Anything on those tips people want to talk about? Ask any questions. Okay. In this case, I'm going to move on to the gotchas. So these are kind of things that have bit me in the arse at some point, and they can generally be quite nasty when they do as well. These things, there's only really 4 of them, but these are the 4 ones that have really hurt me in the past. First one actually is pretty obvious when you think about it. We all like TDD here, and we're big fans of it. It's good, great. But one thing that's true about when you're talking about thread safe and whether objects can handle parallelism or asynchronous and stuff like that, is that you can only prove that something doesn't work properly. You can never prove that it does work properly. So the classic example of this is, again, the list one that we had an issue with. So we were trying to work out whether 2 threads sorting a list would cause the list to get corrupted at the same time. And we spawned up a couple of 100 threads, big massive list, got them all to sort the list at exactly the same time, even used a little nice bit of code that I've come about before, which kind of increases the probability of collisions happening, which I might put in a gist and add to this actually, send around to people. It's quite a useful piece of code. And it worked fine. The list was always sorted correctly. It didn't matter how big the list was. You were there actually for that.
You were, yes.
Didn't matter how big the list was, how many threads we threw at it, always worked fine. Put it in live environment, basically died every time. It's like, we tried to break it as hard as we possibly could. Didn't break. Put it in live, fell over pretty much straight away. You can never actually test that something isn't thread safe. It's thread safe. Although there is a nice tool which I'm actually which Microsoft wrote, which is the one exception to this. What's it called? Damn, I forgot the name of it already. Thread testing software. There we go, Chess. Microsoft Chess. So they wrote this really, really cool thing called Chess, which unfortunately they stopped supporting, which is a shame. What this thing does, and it's occasionally really useful if you really need to battle harden a particular object and you really need to be thread safe, because you kind of find an environment it still works on. And basically what you do is you write a bunch of unit tests for your object, test the behavior, and then you give it, and then you write those tests such that they have hundreds of threads or whatever, or actually just 2 threads is generally enough to reproduce the issue. 2 threads interacting with the object at the same time. And what it does is it actually it artificially controls the task scheduler, the thread scheduler. So it says, oh, at this point in the code here is a likely point that if it's switched it will cause bad behavior. It's very cool, and it would execute every possible combination of task switches for those tests. And it's absolutely brilliant. Found loads and loads of bugs in some code that we thought was. They've been running for years, we've never seen a single failure on it, and it found loads of bugs in it. It's an absolutely brilliant piece of kit.
Does that scale well? I would have thought that trying to find all possible combinations would.
Well, you have
to.
Yeah. If you give it something really complicated, it will run for days. Generally, you'll just, again, if going back to my best practice of earlier, of putting things in a box and controlling it there. Generally, you would only test that box. This, so you'd write some unit tests for the box, and then you throw this at it, and then you've only got a limited number of task switches that can happen and stuff like that. And it's absolutely brilliant piece of kit. I really wish they'd continued supporting it, because it's fantastic. It's the only thing I've ever seen that can actually give you real confidence that it's thread safe. Generally, the only way you can find something that's thread safe is by getting as many people to look at the code as possible, and just the more people look at it, the more people say it's alright, the more confident you can be that it is right. Couple of minutes left. Okay, so I'll rattle through these fairly quick then, so we can finish and there's the discussion in the end. So second one I've got in the gotcha is mixing blocking and non-blocking calls can lead to deadlock. So a bit of experience I've found that if you have basically asynchronous and synchronous code, or blocking and non-blocking code, which is pretty much the same thing, if you mix it within the same code base or the same unit, it can cause all kinds of pain. If anybody's tried to make an asynchronous service call in ASP.NET without making it an asynchronous, what's the word I'm looking for, asynchronous controller. So in MVC you have you can have controller methods be asynchronous now on versions. If you actually try and have a non-synchronous one and call another service asynchronously, it'll never return. And that's because the way the task object works, the way ASP sets it up, it says whatever asynchronous operations go on for this request, always execute any callbacks on that thread. So if you then do something asynchronous and then wait for it, you'll be waiting for it to come back, but it will never come back because you've got that thread held, so you'll deadlock the system. Beautiful piece of functionality. And you find this all over the place. The more and more experience you have with mixing these things, you start to realise it's a lot easier to just go. Actually, this is more like a best practices now, isn't it? I've said that. It's a lot easier to just do everything should be blocking or everything should be non-blocking. Just be a lot of pain. Okay. The last one, the third one here, something that very few people know, but it's actually true in almost every case in .NET, although Node has, because it's a single thread, actually has ways of getting around this. If you have an object that has an event on it, and you subscribe to that event, and then you unsubscribe from the event later on, it may still fire after you've unsubscribed. You may still get the event fired to you if it comes back. That's because of the way events work under the hood, because they always fire on a new thread or a thread pool. It's actually possible for you to say, unsubscribe to this, but the unsubscribe hasn't finished, and you get the event fired. Or that feels like it would only happen if you sort of executing the unsubscribe, but actually because threads could switch multiple times, it can actually happen sometime later as well. The gist of that really is that is if you do unsubscribe from an event, don't kind of artificially start tearing down your handler, or put some little check in there. I know a lot of people like to null lots of internal variables and stuff like that when they dispose objects. Generally that's a bad idea, because you'll end up throwing null reference exceptions in event handlers and stuff like that. So, and it doesn't help the garbage collector in the slightest, despite what some people seem to think. Okay, and the last one actually isn't true now in the most recent version of .NET, but one thing that's caused me a lot of pain in the past was I think it's up to 4. If you use a task object in your task, which is a wrapper around an asynchronous thing. It's a bit like a promise to .NET, to Node developers, very similar to a promise. If it throws an exception in there and you don't handle it, so you don't put kind of a continue with an exception or whatever, or which is the kind of the equivalent of a fail or whatever on promises, or then with an error handler. If you don't put that on, then what it does is when it comes to garbage collect the object later on, it puts it on when it comes to finalize it, it actually rethrows the exception on the finalizer thread, which is the thing that kind of tears down all non-managed, non.NET things that you may be controlling in your code. And that can only ever kill your process. There is no way to recover from that. It just kills your process instantly. And it doesn't give you you can't go out put in logging or anything like that. It just dies, and you sit there going, why the hell has it died? It does nothing. Luckily, someone slapped them around the back of the head and told them this was a stupid idea, and .NET 4, it now kind of swallows them quietly, which could be considered bad as well. But they only had 2 options, and they picked the really, really bad one. So after a bit of slapping and people complaining, they checked the only slightly bad one. So it's just something to be aware of. The way to avoid that is to make sure you always handle errors on your tasks. It's pretty much exactly the same thing in promises. Always handle your errors, because as we've known from what Remy told us last week, you can bring down the whole process in the same way actually if you don't handle the error. Okay, that's my lot. Any questions, things generally people want to ask, not even necessarily I've talked about, but I've bored you all stupid. As I said at the beginning, I had a fair bit of experience with this stuff, so feel free to come ask me questions if you have any problems with anything you're doing with this stuff. I find it quite fascinating, quite interesting as well, so I'm unlikely to say to go away. If anyone wants to just talk about things in the future, just come to ask me. Thank you.
Thanks very much.
Thank you.